This shows the color coding of the three-phase scheme, which we've called a 666 machine. And as you can see, the white goes around clockwise. In the background is on the first layer, and the second column is on the second layer, and the third column facing us is on the third top coil. These are wired on series for each phase. Now, if this was to be done, the net result of the three-phase mutual induction will be to decrease the impedance of that phase. What we've done here is we reverse the polarity of every middle coil by wiring so that it reacts at a 60-degree phase angle rather than a 120-degree phase angle, both on the top and bottom coils. The net result of this practice then is the mutual inductance increases the impedance of the phase instead of decreasing it. This we call the 666 machine. Now, what we've done is we've got the pancake coils, and they are coils of maximum mutual inductance. So in this experiment we can see what is the best gain that we can have from mutual inductance by using the 666 machine. Now we come to the readings. On the readings themselves, what we found out and we're going to look at is that VI, the internal voltage caused by the resonance, the series resonance capacity attached to it, these form three inner quantities. On a piece of paper, you can also meter, read, and draw out the differences of voltages between them quantities. And as we can see, the top VI is going upwards and the other voltage vectors are going downwards, and we have two large voltage readings in between them. And that three sets of voltage readings are what we're wanting to look at in order to form a conception of what the phase angle change has been from the 120-degree input. This type of system causes cycling effects, meaning that the AC voltages will not be constant. So in order to draw this diagram out, we have to do a video whereby we can see on the screen all 6 VI quantities and all delta VI quantities simultaneously. Well, what we're going to do now is go in there and turn on the machine, put up a sound break, and look at all the quantities. First, before we turn the field on, and then afterwards we're going to turn it to a 5-volt field. It looks a little glary. Still looks a little glary. Let's try removing the halide background. As one can see, we have inputs of 0.13, 0.67, and 0.57 on the stator lines. Our phase amperages need to be readjusted. There's our phase amperages. There may be a problem. We'll go over here to the other side. And from over here is where we want to make our crucial observations. And as usual, we got noise in the neighborhood. Next door neighbor's mowing again. Okay then. These are the quantities that we want to make our drawing from. On the top right, on the left there, we got 0.3 volts being increased to 4.07 volts by its resonant rise V, 1 V sub I. And the next one we got a full volt enabling 8.2 volts. And then on the third phase, we got 0.4 volts enabling 4.4 volts. And on our observations, we want to be able to look at those 3 meter quantities on our delta VIs. So we can see that we should be able to see 4.9 volts to the right. .2 volts in the middle. And 4.13 volts on phase 1, but we can't see the bottom meters. We're going to hope that does that. We got 1 volt on 1-3, 12.3 on 1-2, and 12.8 on 2-3 stator lines. Gonna turn the field on now. Okay, now those are our quantities where we want to form a vector diagram from. And as you can see, when we turn the field on, the process became very cyclic. Quantities go up and down rapidly. That's why we need to have a video camera so that we can look at any one particular point cross section in time and be able to compute the phase angles by diagram or preferably by the law of cosines. Now we'll come over here and look at our input quantities over here. And decidedly the whole process is very two-phased rather than three-phased. Okay, now what we're going to do is we got an inductor over here. Finish this out. Where's that inductor at? Excuse me. We got an inductor in space sitting next to the system. It's hovering right around 6 volts, almost a milliamp, and that's picking it up by the adjacent proximity. Now we're going to look at our amperage consumption of those phases, and we're going to place that inductor on top of the system. Glare is apparent. There's sunlight, I don't know. Doesn't look like we can see anything. lot of glare on that meter there. Why? That's better. Now we're going to place the inductor, secondary inductor on the system. Note the changes of our inputs. Secondary inductor on the outside is receiving 1 milliamp with a 7-volt input. Go ahead and move our checklist here. There. 48 there. 68 there. Okay. Secondary inductor is now picking up 300 and some volts cyclically. I'm going to put it in the middle. See what happens there. I'm going to try the far enough. We have the secondary placed on the bar coil. We're going to raise that secondary up again. And note, start off with, we got 0.38, 0.31, and 0.1 on phase 3. Now we're going to raise the inductor. Cyclic, very cyclic activity. Notice that on phase 3 we only have 0.11 amps. We raise the inductor. System resumes to normal readings. We'll now place the inductor on our coil. That's the readings that we got when it's powering the load. And to end it here then, excuse me, there's what the load's picking up. 65 to 69, 70 milliamps, 400 and some volts, very cyclic. And that should call it.